Hello students, welcome back. We just completed section 1 in which we studied arithmetic functions in general. Now let's go to section 2, which considers one specific example, rather two specific examples, the sum and the number of divisors functions. As a matter of fact, we can argue it's just one example. You see, tau and sigma are both coming from sigma k as special cases when k is 0 and k is 1 respectively. So you can put these two together as a single example almost all the time. Okay, that was a quick reminder on the definition. The first topic we'll discuss is the product formulae. Suppose that we have a prime factorization of n. Then tau of n can be calculated like this product formula and sigma n like this. This one is simpler, and actually even the proof is pretty simple too. It's just a combinatorial argument. In order to have a divisor, we have to have a prime factorization only among these. If the potential divisor has any other prime factor, then it will not divide n. Also, the powers should not exceed n. If it does, then the candidate will not divide n. In other words, the P1 has possible power 0, 1, 2, 3, 4, 5, 6 up to n1. So there are total n1 plus 1 choices. And P2 has possible powers 0 and 1, 2, 3, 4 up to n2. Possible choices and 2 plus 1 choices. The same thing continues all over. Multiply them all, that many choices. So it's a combinatorial argument. Indeed, here's the proof. Here's a divisibility condition. D has to be less than or equal to n for each index. Or 0, then I'm going to get 1, the trivial divisor, and all equal to n, then we're going to get the same as n. Each power has ni plus 1 choices because d should be selected from 0 to ni. Therefore, multiplying them all, we get the desired formula. Okay, the proof is simple, but let's talk a little bit more about the notation issue. One way to express the prime factorization is to do this dot dot dot. Another way is to use finite product expression using capital Pi. But there's still a different method, using an infinite product expression. In this case, remember, these PIs are different from these PIs. Here, P1, P2, P3 up to Pk are just first prime, second prime, up to kth prime factors of n. Here, each PIs, those are the list of all prime numbers in increasing order. The first prime P1 is 2, second prime P2 is 3, and third prime P3 is 5, and then 7, and then 11, and then 13, 17, 19, 23, and so on. And then there are infinitely many primes like that, so except for finitely many exceptions, all the ni should be 0, so that we have a bunch of 1s multiplied. Otherwise, you're going to get infinity there. So, except for finitely many exceptions, all the ni's are 0, which means these are a bunch of 1s, and also that's 0, so these are a bunch of 1s as well. So either way, they all make sense. But one critical thing, these PIs and those PIs mean different things, so remember that and do not mix them up. If you have to mix up those two at the same time, then usually it's going to be better to use different characters. But here, I just abused with the same characters here. Sorry about that, but those are common. Otherwise, we're going to run out of characters. We frequently do that in number theory, even worse in algebra. Okay, let's go to 2.2b, and this time we have a product of, do you recognize these? These are geometric series formulae. Remember those? So those are products of the sums of geometric series. Series itself is plural, so many geometric series formula basically. And the proof is based upon that too. The first one here is first geometric series formula. Okay, so first geometric series, sum, and the second geometric series corresponds to the second formula, and the kth, like that. Now, how do you break up all those parentheses? Basically, an extended FOIL method. Anything arbitrary from among those, so p1 to the d1 power, where d1 is arbitrary, from 0 to n1. Anything from here will give you this, dot, 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 dot. Anything from here will give you that. And then each of those powers will be coming from 0, 1, 2, dot, 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 up to n. So that's what you're going to get. The i's are being selected from 0 to ni. So in short, what do you get? We have a prime factorization where all the prime factors are those of n's, and then the powers are less than those of n. So what do you have? This is a divisor. And as a matter of fact, by selecting all these arbitrarily and considering them, all of them, adding them up, we're just taking all possible divisors and adding them up. And that's the definition of sigma n. So that's how you can prove the second product formula. Also remember the special case. If you have just one prime factor, p to the nth power, then we just have a product of one parentheses, the product of just one geometric series formula. Okay, we went through product formulae, and then let's think about an application of that. The multiplicative property. The functions tau and sigma are both multiplicative. Wait a minute. We already know that. We already proved it in section 1. First, we established this general theorem. If small f is multiplicative, and so is capital F, defined like this. After proving this, which was significant, and then we went through these to establish tau is multiplicative, sigma is multiplicative, and also sigma k is multiplicative. Remember that? Here, small f for each of those is constant function, so clearly multiplicative. So we already know tau and sigma are multiplicative. Why do we have to prove it again? Well, reason number one, the multiplicative property is such an important property that doing it twice will not hurt you. It's important enough for a review. Second, I'd like to have reviews of these. That's the second reason. All right, let's prove those. The proof is actually very, very easy. M and n are relatively prime, so m can be decomposed like this with p's, and n can be decomposed like this with q's, where p's and q's are all different. They're all different. They don't mix up. No overlap. If there is, then m and n will not be relatively prime anymore because they're going to be sharing a prime factor. So what is tau of m? Well, that's from this formula here, and that's blue, all right. And what is tau of n? And that's going to be red, coming from this formula. And what is tau of m times n? And that's coming from, let's see, prime factorization is just this thing times that thing, because there's no overlap or anything like that. So that's blue bunches, and then red bunches, all multiplied, consequently blue times red. That completes the proof of the multiplicative property of tau. Just prime factorization. They're all distinct, no overlap, that's important. And exactly the same idea for sigmas. This formula here, that formula again there, and then multiply all the blues, and then all the red. We have multiplicative property. So a lot of dot dot dots, but otherwise simple. Let's see, do we have enough time for example problems? Okay, here's one, sigma of 180. Okay, all right. Let's find the prime factorization, and oh my, I found all possible divisors and added them up. Stupid. Don't ever do this. Yeah, I remember getting all these down while writing this notebook, and I vowed never to do this ever again. Don't do this. I did it only because, well, I'm teaching. Second method, you can use this. For 2, 3, and 5, put those in and run your calculator. A lot better, right? Solution 3, you can use the multiplicative property. Sigma 4, sigma 9, sigma 5, you can find those separately. Which methods do I like the best? This one, of course, the second method. How about the next problem here? N of tau n power divided by 2 thing. So if I square both sides, basically this is what you have to prove. So what you're going to do here is start from the right hand side and then come up with the left hand side. First, let's make this observation. We have all those divisors, and then d divides n, so n over d is a whole number, and d times n over d is n. Therefore, this is also a divisor. Some dj somewhere here, di is here, dj is somewhere there, and then they multiply into n. So if you start from the right hand side, d1 through d tau, number of total divisors, and then the same thing, but the second one, which rewrite those into n over d's. Because these are divisors, and then multiply accordingly, then each time I'm going to get n, and how many total do I have? Tau. So n to the tau power. That's what I'm going to get. And this thing corresponds to the factor rainbow that that you must have gone through in either elementary school or middle school. Okay, all right, so much for that example. And that's it for the first half of section 2. And let's meet again and study the second half of section 2.